Okay, yeah, thank you. Yeah, so today we're very happy to have Rafael Fernandes. I mean, he's no stranger for this series. He gave quite a few talks in this series before. So, but today I want him to sort of talk about sort of a new subject. Previously, he's working on iron-based superconductor. I believe this stuff, at least for now, there's no superconductivity, right? I don't know. It may come.
I'll mention some stuff, but no, right now it's
Okay.
mostly magnetism. Yeah.
Okay, yeah. So yeah, Rafael is very well known to the community, and he has done many wonderful work. So today we're very happy to have him talk about this new concept, which I'm also trying to learn, altermagnetism. Yeah, Rafael, it's all yours. Yeah.
Thank you very much, Benjamin. Yeah, it's great. Actually, I checked that. I think I gave a talk almost exact a year ago on on loop currents in the
on loop current. Okay,
yeah.
Okay.
Yeah. So it's great to be here again. Thank you very much.
Yeah,
and
thank you.
So
thank you.
I'm hoping that with this talk I can share a little bit about this very exciting field of altermagnetism. I'll tell a little bit about my work, but I'll also try to give you some broad introduction on what are the main ideas here. So I'm mostly going to be talking about this first work here that I did with my colleague Turan Birol and my former postdoc Vanildo Carvalho and my colleague Rodrigo Pereira, both from Brazil. And I'm also going to touch on two papers here, one with Jörg Schmal in Karlsruhe and his student Charlie, also in Karlsruhe, and another one with my student Ansuman Chakraborty. Okay, so this is the outline. I first want to start by discussing what is altermagnetism, and then I want to make some connections between altermagnetism and other effects that have been widely discussed in correlated systems. And then for the third part of my talk, I would talk a little bit about our work on how spin-orbit coupling affects these properties. And then finally, I'll discuss some ideas about how to experimentally probe and control altermagnets. Okay, so we all like magnetism because there's a really big landscape of different magnetic orders, and they can give rise to different functionality. So there's this big appeal of new kinds of magnetic order giving rise to interesting applications. And ultimately, to understand magnetism, we need to understand the symmetries. So to explain the symmetries and the idea of altermagnetism, let me go back and ask the following questions. I give you a configuration of magnetic moments. I'm going to be using the word spins, but everything else also works for orbital moments, okay? And then I flip all the spins, so meaning I apply time reversal. And for the time being, I don't have spin-orbit coupling, so I'm just going to distinguish between spin up and spin down as blue and red. And then I ask the following: is there any symmetry of the lattice that I can do to recover my my magnetic configuration that I started with? So let's start with a very simple example of a ferromagnet. So all the spins are up, and now I flip the spins, and then I can ask, is there any symmetry acting on the lattice only that I can do to go back to spins up? Remember, I don't have spin-orbit coupling for now. And the answer always is no, there's not such a symmetry. And we know very well what the implications are. We know now that there's going to be a spin splitting of the bands. Remember, spin up, spin down bands are connected by the operations of inversion, time reversal. In this case, they break time reversal, so there is a splitting, a Zeeman splitting of the bands, and this is well understood and well known. And I'm representing here using the figures from this paper by Lieber, Schmickel, and his collaborators. Now we go to the case of an altermagnet, an antiferromagnet, where I have the staggered spin up and down. Okay? I do the same exercise. I flipped all the spins, so what is red becomes blue and vice versa. And I ask whether there's any crystalline operation that can take me back to this configuration. And the answer is yes. And it's a very simple, it's just a translation, right? Which means that if I combine time reversal and translation, is a symmetry of the system, right? I recover the same configuration. So the symmetry goes by the name T prime. And it turns out that because this symmetry, this composite of a translation, a lattice translation, and inversion is a symmetry, the spin bands do not split, or there's no spin splitting of the bands, and therefore I have no Zeeman splitting. Okay? So far so good. Now, let me take the same square lattice that I had before, and I'll say that for some reason, okay, and I'll discuss the reasons later, But for now, just think that I have, because of the ligand fields for some other atoms in the unit cell, it creates a local environment that is different for the two spin species, okay? Or so for the two atomic species. So what I'm saying is that now my unit cell, instead of having just one atom, has two. And again, this environment here shows that I respect the trigonal symmetry of the crystal, and that's all I did. Okay? Now I can ask the question, same question. If I have a magnetically ordered state, are there any symmetry operations that I can use to flip the spins back or to undo time reversal, if you wish? And for ferromagnets, again, nothing I can do. But now, if I take this configuration with stagger moments up and down, you see now that I cannot do a translation anymore, because actually this magnetically ordered state does not break, does not change the periodicity of the lattice. It's still the same. The magnetic and paramagnetic unit cells are the same. So clearly, it can't be the antiferromagnet that I mentioned before. So what is the symmetry now that can take me, once I do time reversal, flip the spins, what symmetry operation of the lattice can bring me back to where it started? Well, clearly, it's a 90-degree rotation. Okay? So this is not a translation. This is not inversion. So when these symmetries exist, we call this an altermagnet. Okay? And I'm going to go a little bit deeper into this concept, but this idea was introduced again by Hairosinova, Libers, Mikkel in these papers here. So the idea is that configurations with flipped spins, they're related by a rotation. Here, it's a very simple rotation, but it can be improper rotations or other things, as I'm going to tell you later. Okay? But what does it mean? What is the consequence of that? Now, I no longer have the symmetries that make my spin splitting vanish, because it's not a combination of translation and time reversal, but rotation and time reversal. And because of that, I'll have a Zeeman splitting, even though there's no net magnetization. Okay? But there's more than that. What you find out is that the Zeeman splitting, because it's a rotation, the symmetry that is coupled to time reversal, the Zeeman splitting has nodes. And these nodes are related to where to the symmetry. In this case, the nodes are along kx equals 0 and ky equals to 0, like shown here. Okay? So you see that essentially I get a D-wave Zeeman splitting. Okay? So this is how you characterize an altermagnetic state. You're going to have a Zeeman splitting that on average is 0, okay, but it has momentum dependence across the Fermi, the Brillouin zone, right? And I think the key feature of an altermagnet is that you saw from my symmetry arguments, I did not need to invoke spin-orbit coupling. And in fact, you can see that without any necessity to introduce this spin-orbit coupling. And this idea of having Zeeman splitting bands in a system that has zero magnetization and no spin-orbit coupling has been around for a while. So showing here some previous papers. Again, the name altermagnetism is a little more recent, but these ideas have been around. And what is nice from first principle point of view is that you can actually see these splittings in a very, let's say, computationally cheap way, because you don't need to turn on spin-orbit coupling. And you see the splittings here are pretty large. Okay? Now, it's important that the symmetries are rotation. Let me give another example where I actually do not have an altermagnet. So this is just the honeycomb lattice. And let's say that I get Weyl order here. Again, up and down spins, right? And now I ask the same question as before. I apply time reversal symmetry, so I flip the spins. Which symmetry do I have to apply to come back? Clearly, it's inversion. It's not a rotation. But remember, it means that the product now of inversion time reversal is preserved, and it means that I have no spin splitting of my bands. So this case, where the sublattices are connected by inversion, is actually an antiferromagnet and not an altermagnet. Okay? So that's an important difference. So yeah, so here's a summary. And again, I'm following this. Again, this was introduced in this very nice set of PRX papers by Lieber and Heido and Thomas. So here's the summary, right? If I have, so I ask the following question: which symmetries without spin orbit coupling, which symmetries of the lattice when combined with time reversal, leave my magnetic state invariant. In ferromagnetism, there's no such a symmetry. We get a uniform Zeeman splitting. Then antiferromagnet is either translation or inversion, as I just showed you. And then you get no Zeeman splitting. In an altermagnet, it's a rotation. It can be proper, improper. It can be combined with half translations, in which case it is a non-symmetric symmetry. And then what you get is a modulated Zeeman splitting, which can be D wave, G wave, or I wave, and so on. Yeah. Now, you can ask whether there is a sharp formal distinction between these three states. And in this paper here, it was shown that yes, in terms of the so-called spin groups, there are three different spin groups. So most people, or at least I was, more familiar with the magnetic space groups. But in the magnetic space group, you include spin orbit coupling, of course, because you assume that you consider the spins or the dipolar moments to transform as the operations of the lattice. Now, there's something else called spin groups, where the rotations in spin space are uncoupled, if you wish, from rotations in the crystalline space. So essentially a system that has no spin orbit coupling. And there are three kinds of spin groups. Remember, the magnetic space groups, there are four, but here there are three, type 1, 2, and 3. And what, again, this paper shows is that each one of them is associated with a different kind of magnetic configuration. So ferromagnetism is type 1, antiferromagnetism is type 2, altermagnet is type 3. Okay? Now, of course, I will argue later, the moment we have some spin orbit coupling, some of these differences may be a little bit more subtle, but still can be meaningful. What about materials? Where is this realized? Well, I think one of the most known examples proposed to realize that is rutile magnets, which were probably classified as antiferromagnets. But as you can see here, this ruthenium oxide or manganese difluoride, they have 2 atoms per unit cell, and this is related to the oxygen or fluoride local fields. And this is the altermagnetic ground state. And if you look at the spin splittings of the bands, again, even without spin orbit coupling, you have huge splittings, almost of the order of 1 eV. And it actually turns out that there are many examples. So as I said, ruthenium oxide, manganese telluride, they are very large spin splittings, but you have a bunch of other ones here, including oxides, okay, which we'll go back to. And again, this is another very nice paper by Guo et al., where they show a lot of different definitions of spin splitting, a lot of different candidate materials for altermagnetism. So I'll point out that most of these studies, based on first principles, the focus is on having the so-called magnetic atoms, right? So chromium, manganese, copper, cobalt, iron, and so on. Later, we'll go a little bit beyond that. So that's great. There are lots of material candidates. What can you do with that? One of the first, or perhaps one of the most immediate applications, is that you can use them for spintronics. And there are many reasons for that. First of all, you get Zeeman splitting, which means that you get spin polarized currents without magnetization, which means that a magnetic field cannot really affect that much. Okay, and the speed of is also pretty good. So this is one of the applications that have been proposed. More recently, there's a series of papers discussing some very interesting effects that happen when you interface a superconductor with an altermagnet. So for example, think of the standard case of having a D-wave superconductor overlapping or interfacing with a ferromagnet. You can get very similar symmetries by interfacing an altermagnet with an S-wave superconductor. And I'm just not going to go over all these very nice papers, but lots of interesting ideas of finite momentum pairing, topological superconductivity, Marana zero modes. Okay? All right. So now what I'm going to talk about today, I'm going to make a point here that there are many different phenomena that we, working on strongly correlated systems, have been working on that are related to altermagnets. And also, I will explore what happens when you have spin orbit coupling, and I'll show some very interesting effects that happen when this takes place. And please feel free to interrupt me at any time. Forgot to say that. Okay, so let me make some connections between these ideas and other ideas that have been around. So as I mentioned to you, the mechanism, the essential mechanism that those papers and those first principle calculations have focused on is if I have a magnetic atom, right? As I mentioned, iron, cobalt, manganese. And then I have a local environment that are just promoted by the ligands, by the other atoms, okay? Now you can ask whether I can get similar effects from just electron-electron correlations, right? Which is something that me coming from the correlated electronic systems is something I'm interested in. All right, so let me just make an argument. For example, if I start with a multi-insulator, what do I need to do to get an altermagnet? Okay? So it turns out that it's actually not, we know what to do to get that. It's something that is widely known by the name of Kugelkonsky models, okay? So if I do a strong coupling expansion of a multi-orbital system, sorry, was there a question? Okay, so if I do a strong coupling expansion of a multi-orbital system, right, I usually, as we know for Kugelkonsky, we get spin degrees of freedom and orbital degrees of freedom. So imagine a situation where the spins want to be antiferromagnet, okay? But the orbitals, and here just illustrating two different orbitals, want to be anti-orbital order or antiferro-quadrupolar order, okay? Then you can see that because of the orbital order, I enhance the size of my unit cell, and because of that, what used to be called antiferromagnetism in combination with antiferro-orbital order will give you altermagnetism, okay? So this is one route where this can happen, all right? There's also another very nice connection with multipolar moments. So let's just remember classical electromagnetic expansion of potentials, right? My main unit here is a dipole moment, right? I can have a magnetic dipole. Here I draw a quadrupole and an octopole. Okay? You can immediately see that these are connected to the three different states that I have, right? If I have one atom per unit cell, ordered magnetically, I get a ferromagnet. If I have two atoms per unit cell, and they are related by inversion, right, with alternating spins, it's exactly this. It's a magnetic quadrupole. And this is an antiferromagnetic state at Q equals 0. Now, this one where I have alternating between, the spins connected by inversion have the same direction, but the ones connected by rotation, they are alternating. That gives you the altermagnet, and that's a magnetic octopole, okay? So you can see that there's a nice connection between altermagnets and higher order multipoles, okay? And this connection here has been made by several people. There's this very nice paper by Nicole Spalding, and again, in an earlier paper, again, by Lieber Schmickel and collaborators, you get this general idea that you can describe these altermagnets as even parity, higher order magnetic multiples, I'm sorry, okay? And again, it doesn't need to be an octopole. You can have some toroidal moments, like a magnetic toroidal quadrupole, as we also point out in this paper here, also works. But then you can come back and say, can I get multi-insulators that host atomic multiples? And that's very well understood from some systems that have strong spin-orbit coupling, okay? So for example, let me take, this is a D wave, this is a D orbital system, but it's a 5D, so we have large spin-orbit coupling. So it's a double perovskite, okay? And it's a J equals 2, and if you look at the crystal field splittings, the atomic ground state is this EG, okay? Which in this group, if you ask, oh, I have then a pseudospin in this non-Kramers doublet, I'll get precisely a magnetic octopole as one of the combinations of these two wave functions here, okay? So this is one route. So in this case, you can really think as locally having emergent multiples coming from the combination of spin-orbit coupling and crystal field. Here's another one. This is an F electron system. This is a cage compound that has praseodymium, titanium, and aluminum. This is a J equals 4. And on the crystal field split, you get again a non-Kramers doublet. And if you write down the pseudospin, you see that the different components, they transform either as electric quadrupoles or nematic, and one of them as magnetic octopoles. And there are several very interesting papers by Ian Fisher, Yamba Kim, and others talking about this material as well. So you can think of this as also being described in the same framework. Okay, that's good. So I hope I convinced you that you can have also the route of getting altermagnetism via strong correlations. But the other question is, what about if I start with interactions that are not so strong? I start with a weakly to moderately interacting metals. Can I also get an altermagnet? And to answer that, we can go back to this description of multipoles. And instead of thinking of multipoles in real space, as I was doing for Mott insulators, I can take my spin density of my wave function in a metal and expand around the gamma point. Okay? If I do that, I can expand in spherical harmonics, for example, or in lattice harmonics. And when I do that, I can get terms that are higher order. I can get terms that are multiples, higher order multiples. For instance, if this here is a D-wave form factor, any even parity larger L multiple, okay? And again, this doesn't mean that I have multiples in real space. This is a multiple in momentum space, okay? So yeah, every spherical harmonic of rank L results in a multiple of rank L plus 1. And this is precisely connected to something that has been studied for a long time, which is called the Pomeranchuk instabilities of a Fermi liquid. So if you take a Fermi liquid and you ask about the excitations of the Fermi liquid, right? So the excitations are long-lived quasi-particles, and then you can classify, you can expand interaction between quasi-particles and spherical harmonics, and then you get a bunch of instabilities in different channels. Could be the spin singlet channel, spin triplet channel, with different angular momentums. And then you have a condition, a criterion for which this, based on these interactions, the Fermi liquid is unstable towards these instabilities, and they go by the name Pomeranchuk instabilities. You can think of them just as generalizations of the Stoner criterion. Okay, L equals 0 and triplet is exactly the Stoner criterion. Okay, and if you think of these Pomeranchuk instabilities, you're going to see several things that we discuss a lot in correlated systems. So if I focus on the singlet or charge sector, and this, you know, we can go back here, very nice paper by Oganessian, Kivas, and Friedking. L equals 0 is just phase separation. L equals 1 would be ferroelectric metal. So you see now that under this instability, the Fermi-surface breaks inversion, right? But L equals 2 is quadrupolar order, is nothing but the nematic that was discussed in this paper, right? So you can do the same exercise in the triplet sector, okay? And then L equals 0, again, using the Pomeranchuk notation, L equals 0 is ferromagnetism. You get a spin splitting of the Fermi surfaces that is uniform. You can get L equals 1. This would be a P-wave ferromagnet or a loop current, for example. Or you can get an L equals 2 spin triplet, which, again, you get a Zeeman splitting that has different signs for different distortions of the Fermi surface. And that's precisely the altermagnet, right? This kind of Pomeranchuk instability was discussed very recently in this paper by Friedking and Kai Sum and Kong Jung Woo, where there are very interesting excitations. And in those papers here, this was named nematic spin nematic order, is an ferroctopolar order, or we could also say this is an example of a metallic altermagnet. But remember, this is different than the kind of altermagnets I've been describing before, which come from, it's not a spontaneous symmetry breaking of in that channel, but you have these two, well, it is a spontaneous symmetry breaking, but it comes from a ligand that makes the two atoms different in the unit cell. And yeah, so that's what I just said, that this is precisely the D-wave Zeeman splitting. So you could say that any even parity, larger than 0, of course, spin triplet Pomeranchuk instability will give an altermagnetic metal. And as I mentioned, there have been lots of interesting studies about the excitations of this nematic spin nematic phase, the alpha phase, the beta phase, and that translates precisely to these ideas that I've been discussing before. So yeah, so this closes some of these ideas of how to have different mechanisms for altermagnetism. and how this connects ideas that already have been discussed in different contexts. As I mentioned before, you can think of an altermagnet as a D-wave, quote-unquote, ferromagnet. Again, it's not a ferromagnet, but you can think of taking magnetization, tucking in a D-wave form factor, and you can interpret like that. Okay? And indeed, you can, in this classification here in this paper, you can see that you get D-wave and G-wave, and in principle, you could also get I-wave altermagnets, okay? And this gives an interesting connection with superconductivity, right? So superconductivity, you get a D-wave, a conventional superconductor, a D-wave, you get a D-wave gap, you get nodes on the excitation spectrum. In an altermagnet, it is the splitting of the spin up and down bands that acquires the D-wave form factor, okay? And you get this. And you get nodes in the Zeeman splitting. As I'm going to argue, this is an interesting analogy, but it's a little bit incomplete. Okay, so here gives me an interesting overview of how I can go over or connect altermagnetism with a correlated electronic system, from metals, where I get Pomeranchuk instabilities, to insulators, where I would have orbital order or multipolar magnetism. And if you want to try to focus on correlated materials that can be altermagnet, one that immediately comes to mind are the perovskites, okay? AbO3 perovskites. Many of them are Mott insulators, and they display Weyl type and ferromagnetic order, alternating spin up and down, okay? And we all love them and are familiar with them, the cuprates, manganites, titanates, rutheniates, vanadates. Now, an ideal perovskite has this cubic unit cell, and this really is an antiferromagnetic order, okay? Now, a lot of the perovskites, actually, they're not really cubic, but to accommodate this A atom, this oxygen octahedral, they actually have to rotate, and they rotate in a staggered way like shown here, okay? In this case, the actual symmetry of this perovskite is orthorhombic, and the space group is the well-known PNMA. And we can actually look again now what happens to my Weyl order, my staggered order in the PNMA structure. And here's what you see. This is the ideal cubic lattice, okay? And as you can see, the paramagnetic unit cell, which I show here by these solid lines, solid black lines, is different in my magnetic unit cell. Now, once I include the octahedral rotations, and now I'm showing here in the plane the effect of these octahedral rotations, you see that the paramagnetic unit cell is equal to my magnetic unit cell. Okay? So there is a chance that this is no longer an antiferromagnet, but an altermagnet. Okay? To see that, let's do the exercise that we've done before, right? So I'm going to take the octahedral rotated unit cell, okay, with these two kinds of atoms. Again, these are the B atoms, up and down spins with blue and red. I apply time reversal. I just flipped red and blue. Now I ask the same question: is there any symmetry operation that will take me back to this configuration? So obviously one of the things that you want to do is do some rotation. So let's take this axis here, and I'm going to do a 180-degree rotation, meaning this red is going to go down, this blue is going to go up. So here's what happens after you do this rotation. I didn't quite get where I used to be, but that's because there's one ingredient missing, which is a half a translation, okay? If I do half a translation, as you can see here, now I get exactly where I started. So this is actually a common theme when you look at the full crystalline structure. 100-degree rotation plus half translation is a screw axis. Again, it's a rotation with something else. So it is an altermagnet. The point is that in a lot of these materials, the symmetry is really usually a non-symmetric symmetry that leads to that connection. And so this shows that if I have Weyl ordered perovskites, they could be candidates for altermagnets. And here's just showing some how they spin up and down creates different environments. And as we know, a very interesting candidate are the rare earth titanates, because you can control the kind of magnetic state, Weyl or ferromagnet, just by changing the rare earth element, because the changing radius changes the octahedral rotations. All right. Okay, so now let me talk a little bit about what happens when we have spin-orbit coupling, right? So as I mentioned, you do not need spin-orbit coupling to get a Zeeman split. That's good, but spin-orbit coupling is inevitable, right? So even if it's weak, it's there. And the main effect of spin-orbit coupling is that it ties rotations in real space with rotations in spin space. So look at the spins here, put spin pointing into the plane, up or to the right, and here do a 180-degree rotation axis. If I now rotate the spins with respect to the axis, you see that now, depending on the direction of the spins, right, if they are not parallel to the axis, they will also flip. So there is this connection now that I can't ignore. So, and we know that in ferromagnets, spin-orbit coupling is very important because it forces the moments to point along certain directions. So the question we ask is, what happens in these altermagnets? Do we get, what is spin-orbit coupling doing? To do that, we're going to do some group theory. So let me tell you the result, and then I'll go over some of the details. So what we find is the following. We can't really think of the modulation of the spin as all the spin components have the same angular modulation, but each component will have a different, generally a different modulation. What I'm trying to say is that spin along Z will have one kind of D waveform factor, along X, a different D waveform factor, and so on, okay? And I'll go over how we arrive at this conclusion, but let me just tell you the consequences. This means that there's no way that I'll have a purely, entirely collinear altermagnet. It also implies that some altermagnets will trigger weak ferromagnetism. It has also implications on the symmetry classes of these altermagnetic transitions, and what happens to those, it has implications on the symmetries of those Zeeman splitting nodes. Okay, so to explain how we get to these conclusions, let's consider a very specific case. We consider I can combine all of them, and right now my spin density as now not a D waveform factor, but as a D vector, and each component of the vector transforms a different D waveform factor. So for example, sigma Z has Kx, Ky, sigma X has Ky, Kz, and so on. The zeta here is just to show that the coefficient of this does not need to be the same as this. Okay, so this is the first indication that the moment I turn on spin-orbit coupling, I'm going to get spin modulation along all directions. So it's not a collinear problem anymore. You can say, okay, well, how do I see that in real space, right? So let me take the case of a rutile. It could be ruthenium oxide that just shows manganese difluoride, right? And here's what we can do. We can, to look in real space, we can look at the so-called Wyckoff positions, and we can ask at the magnetic Wyckoff positions, actually, and this tells us which direction the magnetic moment can point. If you look at manganese and fluoride, which are positions 2A and 4F, you find here that they can only point along the Z direction, which seems to contradict what I just told you, that the moments have to be non-collinear. What is missing? Well, what is missing is that you have these empty Wyckoff positions, which you call X, and in that empty Wyckoff positions, you can see that the moment can no longer be along Z only. It is going to acquire components in the plane. And in fact, if you draw these in-plane components, you get precisely this octopolar nature that we discussed before. Now, these are empty Wyckoff positions, but remember, the wave functions are not localized in the manganese or in the fluoride. They actually spread, and therefore they have to have, when they overlap with these positions, they will have to have the symmetry. So this is just another statement that every altermagnet, when I turn on spin-orbit coupling, will have a non-collinear structure. Okay? If you still don't believe me, you can look at actual first principle calculations. So these are these panels here on the right from this paper by Guo et al. You see that when I have a finite KZ, I don't have only spin polarization along Z, I also get some component along X. You can do something more generic, where you say, okay, I'm going to introduce my low energy model, where I couple my altermagnetic order parameter with my spin operator, and of course I have to now use that D-wave vector. And what happens if you just diagonalize the Hamiltonian is that if I start with a single Fermi-surface, circular Fermi-surface, it splits in two, and you see that the spin polarization is only entirely SZ along the KZ equals 0 plane, because then these two coefficients cancel. Everywhere else, you're going to have mixture of other spin components. Okay. Now, for more complex structures, and here's here's one of the perovskites, one of the PNMA perovskites, like calcium manganese O3. You see that even the occupied Wyckoff positions will have non-collinear magnets, and that's well known. If you do DFT calculations, for example, and you see the dominant order is the Weyl order with spins alternating up and down, but you acquire small magnetization along other directions. Okay, very good. So this is all when I chose the spin. Remember, I said I had kx, ky, d-wave form factor. I chose the spin to be along Z. What would happen if I had chosen the spin to be along the plane? So in this case, these two combinations transform kx, ky, sigma y and kx, ky, sigma x. They transform as the two components of the so-called EG, right? But it turns out that the spin itself, sigma x and sigma y, also transforms as the EG, right? So what does it mean? If I have, in this particular case, a D-wave altermagnet with in-plane moments, I will necessarily induce a ferromagnetic component. Okay, and in this case, of course, you see, I will, if I have predominantly altermagnet coming from modulation of sigma y spins, I'm going to get spin along sigma x, meaning it's a canted moment. Okay, so these states, we call this an altermagnet that is mixed with a ferromagnet. Right now, you see, these all happen once I turn on spin orb coupling, and you can say, well, so why call this an altermagnet if it has a ferromagnetic component? Well, it's a matter, I think that in this case, a matter of energy scales, right? Both are going to give spin splittings, right? This is going to give uniform, this is going to give a modulated. As long as this is much larger, for example, than this one, you can still, I think, attribute most of the physics to altermagnetism and not ferromagnet, but it's a mixed state. Now, this gives rise to interesting ideas. And for example, if you take the rutiles, they have the moments point out of the plane, so they don't have a ferromagnetic moment. But if you rotate the moments by applying an in-plane field, and this was discussed, I'll discuss this again. There's another paper by Sinova and Smejko and collaborators, you'd get weak ferromagnetism. This also has an important consequence for the perovskites. You only get a pure altermagnet if the moments point actually along the a-axis, as I'm showing here. If the moment's pointing any other axis, then it's going to get a small ferromagnetic moment. And in most, for example, in the rare earth titanates, these Weyl vectors always align along the c-axis, which means that these are not pure altermagnets. All right. So you can derive these D waveform factors, or these D vectors, if you wish, for all the different point groups, irreducible representations, and we have an extensive table of that. Now, of course, the altermagnetic order parameter transforms as one of the ERAPs, and they'll give rise to either Ising or six-state clock universalities. Notice also that the form factors do not need to have the same symmetry. So, for example, B1G minus in the D6H group, it has the in-plane moments have D wave form factor, but the out-of-plane moment is actually a G wave. Okay? And this is all because of spin-orbit coupling. And then actually, I think it's good to revisit now that analogy we did with superconductivity, I would claim that that maybe a more precise analogy would be with a triplet superconductor, right? Because now I have my altermagnet is d dot sigma, which is the same structure you get in a triplet superconductor. Of course, this is now in a Ambu space. And because of that, you add the two terms in quadrature. But you see clearly that the main difference here is that this d wave, this d vector, is even parity for the altermagnet, but odd parity for the triplet. Okay, so there's this, I think, this interesting analogy here. Okay, now I want to focus on another very important consequence of spin-orbit coupling, which is on the Zeeman splitting. As I mentioned, Zeeman splitting in an altermagnet has nodes, right? Let's take a case without spin-orbit coupling here. The Zeeman splitting has just the D-wave form factor, so kx, ky, and if I solve the equation kx, ky equals to 0, I get two planes, these two planes here. So I have two nodal planes. Now let's take the same example and now turn on spin-orbit coupling. You see now that the Zeeman splitting is now the absolute value of a vector, which means that all components of the vector have to vanish. And this actually turns out that you can always find a solution in this case. If you want to solve these three equations, for example, you can solve it by having kx equals 0 and ky equals 0. And so what you see is that these whole planes, these nodal planes, they are now reduced to three nodal lines. Okay? And this is an important property. And it's actually generic. I just want to show that we actually did a calculation. And for most of the ERAPs, you get nodal lines, not nodal planes. But this actually has very important consequences for the topology and symmetries of the system. Take, for example, let's take a very simple example of just spherical Fermi surfaces, and we have now this d wave, this d vector, and let's see what happens. We have again three nodal lines. They're shown here. Okay, when these nodal lines cross the Fermi surface, they give rise to pinch points, right? These are points on the Fermi surface, as you can see more clearly here, that are not actually split, right? And I'm showing here one of the pinch points. If you go, you can see it here where the spin up and spin down bands cross in this point, okay? Now, if you expand the Hamiltonian around these pinch points, you get a very familiar Hamiltonian. You get exactly the effective Hamiltonian of type 2 Weyl nodes. And if you compute the Berry phase, you get plus or minus pi, okay? Now, this is a nodal line that is crossing a surface. That's why you get points. Okay? You can also look in the energy dispersion, and you get exactly the tilted a cone that is characteristic of type 2 Weyl nodes. Okay? Now, if you ask what are this nature of these Weyl node-like points, and actually of the nodal lines, you'll find that the nodal lines are actually protected. They're not topological, they're not protected by global topological properties, but they are protected by crystalline symmetries. It turns out that all these nodal lines, they always are sitting on one of the mirror planes of the crystal. And because of that, they are crystalline symmetry protected nodal lines. What does it mean? It means that if I do small perturbations, I cannot gap out the lines. Okay? So let's understand what it means for a very important effect. Let's say that I apply a magnetic field. Okay? In the presence of a field, you can model the problem as you're taking a new d vector that is the original altermagnet d vector displaced by the magnetic field. Okay? And here's what happens, right? If my magnetic field is applied in an arbitrary direction, it will break the mirror symmetries where the nodal lines were sitting, and because of that, the nodal lines disappear, okay? And you can see that in this case. I apply here a field along this diagonal, in plane diagonal, and if I try to find a solution of d tilde being 0, there's no solution, because I either have to set kx equals 0 or ky equals 0. So this immediately gaps out my nodal lines. Now, if I apply a field here along the z direction, which is perpendicular to this mirror where these two nodal lines are, I can now solve these equations by setting k is equals to 0, and then this equation here gives me a hyperbola. So if the field is perpendicular to a mirror plane, it cannot gap out, infinitesimal field cannot gap out the lines, the Zeeman nodes on this mirror. Okay. What happens actually? Well, what happens is that I apply a field. Here's now in the Brillouin zone, right? You have these closed loops that they no longer restricted to the borders and the high symmetries of the Brillouin zone, but they form these loops. And I'll need a certain critical value of the magnetic field to make these loops collapse into points. And then only after that, I get rid of my nodal lines. Okay? So this means that when I apply a field along a high symmetry direction, I actually keep my altermagnetic properties, right? If I associate nodal Zeeman splitting with altermagnetism and a nodeless Zeeman splitting with ferromagnetism, it means that in the presence of a field along the symmetry direction, the altermagnetic phase survives up to a critical value of the field, and then you have a topological transition to a ferromagnetic phase, okay? And here we just plot the area of these loops, and you see it goes from pi square to 0, and here we show the minimum Zeeman splitting, which is 0 inside the altermagnetic phase, and then increases in the ferromagnetic phase, okay? And this only happens because of the spin orbit coupling, okay? And you can see that because of the same reason, this is the Fermi-surface, a projection of the Fermi-surface in the plane. I apply a field out of the plane. You see these are the pinch points. It's where the Fermi-surfaces of the spin up and down touch. And if I turn on the magnetic field, what's going to happen is that these pinch points are going to start moving. I can't destroy them. They have to move until they annihilate each other. And then I get two split Fermi-surfaces, okay? And this is an analog of the annihilation of nodes in superconductors. Okay, they have to collapse into a single point. Okay, so how much time do I have, Peng-Cheng?
You have like 5 more minutes.
Okay, so I just want to briefly talk about how can we now probe and control these altermagnets. So what I would call the smoking gun would be, of course, if you do spin-resolved ARPAs, and then you could see this D-wave spin splitting of the Fermi-surface, right? So, so you need some probe that can look at spin up and spin down. Of course, you could also use spin-polarized STM, and then you'd see the equivalent of a D-wave superconductor, but of course, it would be a D-wave splitting of the bands. And this is showing the high-resolution spin-resolved ARPAs that is available nowadays. So hopefully this will be something that will be realized soon. There's another interesting effect. Altermagnet on its own does not have an anomalous Hall effect, because anomalous Hall effect requires the presence of a ferromagnetic moment, if you wish. But remember, I said that depending on the direction of the altermagnetic moments, it will induce a weak ferromagnet, which then will enable the appearance of an anomalous Hall. You know, this anomalous Hall without spin-orbit coupling was discussed in terms of something called crystal Hall effect. But the key point is that, remember I said that in ruthenium oxide, the moments point out of the plane, but if I apply a field in the plane, I can rotate the magnetic, the moments, and they will give rise to a Hall, to an anomalous Hall effect. This is also I think this is also what explains this very nice anomalous Hall effect seen in this manganese oxide here, okay? So in this case, you're using the weak ferromagnetic moment to induce an anomalous Hall response. Mm. Now, the other interesting thing is that a large class of altermagnets, they're actually characterized by something called piezomagnetism. So piezomagnetism is the effect by which you apply a magnetic field, you get a lattice distortion. It's not magnetostriction because this effect is linear in the field. So if I change the sign of the field, I'll change the sign of my lattice distortion, okay? So this paper here nicely shows how this manganese telluride, how it has actually pretty nice a piezomagnetic response, okay? Not all altermagnets will have it, but most of them will. And this actually opens an interesting possibility, which we explored here, a magnetic field does not couple to the altermagnetic moments, but in the presence of strain, it does. Now, in any real crystal, we're going to have random strain. So because of that, random strain will essentially enable the altermagnetic moment to see the magnetic field, and you have a physics of the random field IZ model. But in contrast to most materials here, the intensity of the random field is actually, you can control by the external field. And that can give rise to interesting behaviors where you go from altermagnetic to a paramagnetic phase, or from a paramagnetic to an altermagnetic phase. So even though an altermagnet does not couple directly to a magnetic field, it can give rise to these interesting effects. For the same reason, this piezomagnetism you could see a very nice signature of piezomagnetism, or sorry, of altermagnetism by looking at the shear modulus. So without magnetic field, the shear modulus doesn't really care about the altermagnet, or doesn't care much. But if I turn on the magnetic field, now the altermagnetic moment couples directly to the shear modulus, and you should see a softening. And we know that the shear modulus measurements were routinely done in ionic ties. This is nice results from Anna Bommer. So hopefully, again, this will be something that can be done soon. The other thing that you could do is apply strain. So take, for example, the case of the perovskites with the octahedral rotations. These rotations are actually very strongly affected by strain. So you could use strain to control these rotations, which in turn control the size of the altermagnetic moment. Finally, let me just, for the last thing, point out this effect that is rather curious. It's there's a very unusual coupling between the phonons and altermagnets, or altermagnetic excitations, okay? So this is a coupling in which the phonons couple not to the altermagnetic moment, but to the conjugate momentum of the altermagnetic moment, okay? This is different than the piezomagnetism that I told you before, but it's present in many of these altermagnets, okay? So what does it mean? This actually has a very interesting implication. It means that I could, in principle, see the altermagnetic modes in neutral scattering or X-ray scattering by looking at the phonon spectrum. Because, again, the phonons coupled to the momentum is a dynamic coupling, momentum of the altermagnets. You see that if I probe now the response, I'll see this appearance depending on the direction, right? Depending on longitudinal or transverse mode, depending on the direction, I'm going to see these modes emerging from the altermagnet, okay? So this is the equivalent of what's called the magnum polarons, be an altermagnum polaron, okay? All right, so I think I'm done. I wanted to give you a perspective of this field, how the altermagnetism, this idea connects to lots of interesting other concepts that have been around, and discuss also how the presence of spin-orb coupling leads to interesting topological and physical properties of these fields. Thank you for your attention. I'll be happy to answer any questions.
Thank you very much, Rafael. Very nice talk. Yeah. So before anybody else, maybe I can ask you a question. So you can you just repeat what you said earlier in terms of the consequences? I mean, so from a spin wave perspective, I mean, what do you actually expect in terms of a spin wave of one of those potential altermagnets?
For the spin waves, yeah. I'm trying to think if there have been calculations of the magnum spectrum. You can model this. I mean, again, you can model this as just having an intra-unit cell exchange coupling. So it should probably be gapped, right? But there should be clear magnetic excitations. I don't know. I think there was a paper by, I want to say Okamoto and Meyer, where I think so, where they discussed some signatures of altermagnetism in the magnum spectrum, the spin spectrum, directly in the ordered phase.
I see.
I'll be happy to send you the paper. I'm just trying to.
Okay. But a lot of questions. Okay, so let's get Ming to ask a second question.
Rafael, thank you very much. Sorry, that might have been too quick. Can you say a few more words about the piezomagnetic coupling? Does it have to be a random strain field? Yeah.
Sorry, oops. These, you're talking about this stuff here that I mentioned about the coupling. Yeah.
Yeah.
So any strain, if you apply strain, now your altermagnet. So there's a cubic coupling between strain, magnetic field, and altermagnetic order parameter. Okay. So if I have a magnetic field, it means that strain now couples directly to the altermagnetic order parameter. If I apply strain, it means the magnetic field couples to the altermagnetic order parameter. The point I was making here is that in a crystal, because you have random strain in the sample, you actually don't need to apply strain. There will be some effect of a magnetic field. And that's the same effect as a random field. The difference is that now your random field of the Ising model that you have is the product of the fixed amount of disorder you have plus a coefficient that is the magnetic field. So you start changing the magnetic field, you're essentially making the system more altermagnetic disorder, if you wish.
I see. Okay, thank you.
Amelia?
Hey, Rafael, thank you for a wonderful talk. I learned a lot, and now I have a lot of questions.
Great.
I'm trying to think of the image that you used in the early on to introduce altermagnets, that of the rotated polyhedra of each magnetic moment, where it makes it necessary that you have a translation plus a rotation in order to fall
the
back.
half translation, yes,
right?
yes.
Maybe a little earlier on, but this is good enough too.
Yeah.
Yes, my question is twofold. One has something to do with Ming, but let me first ask this. If instead of, do you mind going back a couple of slides to your schematic from earlier on? Because I think I have an easier time making my point based on that.
No, you passed it.
Yeah, I think you passed it.
I passed it. I'm sorry.
One with the square with the four.
Yeah, that's here. Yeah.
There we go.
Oh, okay, sure.
So this schematic represents very nicely rotation or the way that these local environments are rotated to break this translational symmetry.
Right.
I guess my question is, would just some distortion or tilting of the environment, of the local environment, be sufficient, or could that then give rise to altermagnetism?
So I would say that this is usually a good starting point, but you need to make sure that the spins the opposite spins are not related by inversion. So let me give you an example of a case that take the iron-based superconductors that we all like and love, right? You have 2 atoms per unit cell, right? And that has to do with the arsenics going up and down, right? And now if I do not a stripe order, but I do the Weyl order, right, where I have spin up and spin down, you could think, oh, this probably is an altermagnet, but it turns out it isn't, because if you just look, there is an inversion center connecting them. And this was pointed out actually in a recent paper by Igor Mazin. So having the rotations is a good start point, but you need to make sure, because if they are connected by inversion, then they're just an antiferromagnet. They don't have the spin splitting and whatnot. Okay. So there's a little bit of that one needs to do. But yes, looking at systems that have octahedral rotations or any ligands, right, that are locally distorting your lattice to accommodate some bigger atom than other, that is a good, that's what people have been looking at. Yeah.
I guess I could ask you offline or online as it is, but not during this Zoom call.
The other online.
The other online, yes. Some questions related to exactly the point you made right now, because we have some systems that we worked on in the past that could work for this.
I would be happy to. Yeah.
My other question related to what Ming just asked is that regarding strain. I may not be seeing all of the ramifications of this, but I'm thinking that strain, if you had a symmetric lattice, if you didn't have this exactly, if you had something that is symmetric and you then apply strain, does that induce an alter?
So by symmetric, you mean something where the spins are related by inversion?
Yes, or thinking again of the local environment. If the local environment is symmetric,
Right.
applying strain
see.
distort it, but it doesn't distort it. It doesn't produce a rotation necessarily.
So yeah, so the problem, so usually you want this distortion, this rotation pattern to have a wave vector, right? You want it to be staggered. So strain usually is the Q equals 0, so it's not going to be able to directly couple to the rotation like a linear way. But of course, you can, by applying strain, like if you know that these rotations are coming from just like in the perovskite, right? You want to accommodate the A atom, right? You can relieve some of that by applying strain, and then the rotation changes. But the rotation is already existing, right? You're not. I don't think you can create the rotations just with strain in this regard, right? So think of this. Think of the order parameter as or the conjugate field as the product of certain strain and a certain direction of magnetic field. That's what couples to the altermagnet. And now, if you can apply both, great. But if you can apply only one or the other, you can play this game, right?
Mm-hmm.
And it depends, right? These are all. You see, there are some altermagnets that actually do not have this property. They do not have. They're not piezomagnetic, so this would not work. So it's with a grain of salt that I'm saying these things.
Yeah. Okay. Okay. So Liang, you have a question?
Yes, I have a question about the anomalous Hall effect. So you mentioned that altermagnet doesn't usually have anomalous Hall effect, but
Right.
it was reported in magnetolarian. It actually has hysteresis loop.
Which one?
Magnetolarian.
Magnetolarian.
So I believe that in manganese, and I need to check, but my recollection is that manganese tellurium, the moment is that example is not quite that, but is the example I gave where the moments point out of the plane, and they actually induce a weak ferromagnetic moment.
Oh, so you're saying that there's a moment in magnetolarian?
I believe so, but I need to double check. I haven't like a weak ferromagnetic moment that is allowed by symmetry. The key point is that what allows an anomalous Hall effect to exist also allows a magnetic moment to exist. So you can't have one without the other. Maybe the one's very small. And there's an argument to be made that even a small moment can give a large effect because you have this. This is the idea that Lieber, Smiko, and others propose of something that they call the crystal Hall effect, which once you have a field, it makes that in an anomalous Hall effect. But no, just in a symmetry point of view, if you have an altermagnet, a pure altermagnet, without any magnetic moment, you cannot have the anomalous Hall.
Okay, yeah, thank you.
Let me just, I saw that Thomas Meyer actually answered here. Yeah, he mentioned his paper. I think it's in the chat where the number of branches that you see. This is to your question.
For spin waves. Okay.
Yeah, I remembered that he had a paper. Didn't remember which one he wrote the paper here.
Okay. I'll pay attention.
Yeah.
So Junhao.
Hi, Rafael. Great talk.
Hey.
So in the PRX that you mentioned, there's a lot of emphasis that the altermagnet has to be collinear, but there's some non-collinear order which can also effectively induce a magnetic autopolar order. For example, like this manganese 13, which people also observe a piezo-magnetic effect. So my question is that is there any fundamental difference between the collinear altermagnet order and the non-collinear magnetic order?
So depends on how you want to think. So if you want to start thinking on a rigorous way where altermagnet, ferromagnet, and antiferromagnet are completely separate, they can't mix, then you have to turn off spin-orbit coupling and consider only collinear configurations, okay? My point is that even if I start with that assumption, the moment I turn on spin-orbit coupling, I'm going to get non-collinear. And again, it's non-collinear in the sense that you're going to have other components that are going to acquire small modulation. It doesn't mean that, that's going to be the biggest effect, but it will be there, right? So fundamentally, even if I start with non-collinear, with collinear, moments and build my altermagnet from that, it will necessarily, the moment I have a small spin of coupling, acquire non-collinearity. Now, what you're mentioning is, I think, to some extent, is more similar to what I was referring for the case of the perovskites, right? Which, if you look here, this is a non-collinear magnetic configuration, right? And it's an altermagnet, right? So if the moments point along A, there's no weak ferromagnetism. So this is really a truly non-collinear altermagnet, if you wish. I don't know, did this answer your question?
I mean, is this actually seen in the experiment? I mean, in the magnet fluoride, is there actually a component?
I mean, yes. If you look at the rare earth titanates, one way that people actually probe the antiferromagnet, what they call antiferromagnetism, is by looking at the ferromagnetism by looking at the pi magnetic breakpeak, because they're coupled. Yeah, this is well known. There are papers from several years ago by Nicholas Spalding and others showing that you need to get this because of this reduced symmetry. Okay, so yeah, so Junho, I would say that you can start with collinear in any material. It's not going to be perfectly collinear. Maybe the effects of the non-collinearity are small, but as I just mentioned, sometimes this non-collinearity will create a weak moment, and that, for example, give rise to an anomalous Hall that you wouldn't see otherwise. So it's all a matter of how you want to approach it.
Right. So the non-collinearity you discuss here are small compared to the collinear part, right? But the order I mentioned is, something start with the non-collinear, for example, like 120 degrees alignment between the spins in Tagomi lattice. I mean, yeah, go ahead.
Yeah, no, I was just going to say that I don't think, as far as I know, and Libor Smika would be the person that would know this better than me, I don't think you can do, when I think it all boils down to this slide here, and let me just go back. If I want to have a formal mathematical or group theoretical description of altermagnets, is this one here in terms of spin groups. And these I can only, or this category here is only for collinear, like starting collinear. Non-collinears, as far as I know, the same kind of classification hasn't been done. I don't think there's anything fundamentally preventing that. Like, it's just probably a lot of work. But so that's why I think in that paper they were focusing more on these, because these are the cases where you can, from a formal standpoint, describe these three categories separately.
Say it.
Yes. Hello, Rafael. I just want to quickly comment on the fact that there are recent papers from Chen Fang group and Jida Song. They go for very general spin group. It's a very recent.
Beyond just the collinear. Okay.
Exactly. Collinear part is the altermagnet. The other one are just generally a spin group protected magnet. That's what they call.
Thank you. Yeah. So so there's no fundamental there's not preventing it from, it's probably harder and more difficult. And just I saw that Benjamin Franzen had a question about, are there any predictions for the magnitude of the non-collinearity? So if spin-orbit coupling is weak and you start with something that is collinear, you expect that to be small. And in those plots that I showed you, you can use DFT, and turn on spin-orbit coupling to see what's this, and it's usually much smaller.
I see.
But this doesn't need to be, as Junho was saying, if you start with something that is already non-collinear.
Okay. Very, very nice talk. Yeah, generate a lot of interest. Yeah.
Well, I'm glad. And again, I'll be happy to discuss more if anyone wants. And I saw there was another question that was already answered by a few people. If altermagnets, no, they don't need to be insulated. Actually, there's several of them that are metallic.
Yeah. I mean, that's why all the anomalous Hall and all these other things are seen.
Exactly.
Yeah. Okay. Thank you very much, Rafael.
Okay. Thank you. Bye-bye.
Thank you. Yep.